present our work on I'm excited to present our work on DataStates-LLM, which is essentially a very near zero overhead checkpointing method for large language models. So this is a joint work with people from Argonne, Rochester Institute of Technology, and it was presented at HPDC 24. With that, we already know the context that once upon a time, someone invented transformers, and now it is picking up essentially every stream that exists, science and beyond that, right? So as we can see from back when transformers was introduced to right now, the size of these models have been exploding in an exponential fashion. And as these models become larger and larger, they also need more and more resources. And as you can see in the table on the right, they also require more duration, right? So if it takes several weeks, if not months, to train some of these large models. And when we translate it to the unit cost that is required per GPU, we are talking about millions of dollars. And this is not even this does not even cover the cost of debugging the model or doing some dry runs, and things like that. So as we can know, as we see, this entire pre-training of these large language models is extremely expensive, and it is resource intensive, and it goes on for days. So a natural consequence of running them for weeks and months on a large number of distributed GPUs is the probability of failures. So when we run on distributed resources, these large language models that are trained, they are prone to a lot of failures, right? So as we can see in this diagram, which is from a paper from Alibaba, only 56% of the trainings they finish successfully, and the remainder they encounter some or the other form of error, most of which are pertinent to the GPU devices or the interconnects of GPU, which means the NCCL. In the case of NVIDIA GPUs, and there are other high-speed interconnects. So essentially, this means that there might be instability in either the hardware, the software, or the firmware stack that runs and binds it all, right? And we have another case study. This is from Shanghai AI Laboratory, wherein they also report a similar finding, wherein only around half of their jobs complete successfully, and a huge proportion fails, right? So from these traces, we understand that the data centers and the LLMs today, they essentially need a mechanism for fault tolerance, right? And since multiple decades, checkpointing has been a fundamental aspect, for fault tolerance, for recovery, for resilience. So as we can see in this diagram, growing on the x-axis, we have a timeline and we have multiple GPUs. And every diamond red box that you see here is essentially an update boundary, which means that the model was updated, right? So assume that the training or pre-training of these large language models is running on 4 GPUs, and we just configure it to take a checkpoint, which means capture its state after every 2 iterations or 2 update boundaries, right? So as we can see in this diagram, on the second update boundary, we have the blue circles, which means that the model was essentially checkpointed there, or we captured the model state and we persisted it to a stable storage, like a parallel file system, from which it could be recovered and restarted. And as the training progresses, after the 3rd iteration, before we reach to the 4th update boundary, there essentially is a fault, because of which we need to again roll back and restart back from the 2nd iteration. So this means that we end up wasting a lot of GPU hours. And checkpointing, I label this slide as checkpointing as a fundamental primitive, because checkpointing has use cases beyond fault tolerance, right? So for example, one of the scenarios is failure, wherein we are studying what happens when model or the training fails because of some of these errors. The other problem with LLM training is undesirable training trajectories. So, for example, Google Palm, when they were training their model, they reported arbitrary model spikes, which may occur because of floating point discrepancies of the model, or maybe some of the mini batches they interfere in an unfavorable fashion with the training process, because of which we see huge loss spikes that occur at arbitrary moments in the case of training, right? So the only solution they found for recovering from these undesirable training trajectories is to roll back to checkpoints which were taken hundreds of time steps ago. And the reason that these were taken hundreds of time steps ago was that fine-grained checkpointing was very expensive, because checkpointing essentially a terabyte scale model it blocks your training for quite a significant time, right? And the third scenario is also on the front of productive and administrative use cases, wherein we checkpoint or we capture the model states to understand how the model has evolved over time. So it could be something like provenance, or we want to understand, how the ethics have evolved, or how the model is following certain biases based on certain data samples on which it has been pre-trained. So we need to run periodic evaluation suite in the background, right? So again, that demands a more fine-grained checkpointing technique. Or we could have a situation wherein you have an HPC cluster composed of thousands of nodes, each with multiple GPUs. But on these HPC cluster, we cannot just reserve the entire cluster to pre-train a model for months and months together. So we need a capability to suspend these jobs and resume them later. So this comes in the domain of administrative checkpointing, right? Or making it more sophisticated, we could have the notion of an elastic training, wherein we start with a different number of GPUs on which we are training, and then we elastically reconfigure it to, let's say, run on a smaller number of GPUs if the HPC data center needs to be used up for some different applications, let's say a seismic simulation, right? So the checkpointing has evolved with a definition that grows beyond fault tolerance. So, in order to understand how do we efficiently checkpoint, we need to first understand how these models are scaled, with the help of 3D parallelism and more parallelism techniques that have evolved in the last half a decade, right? And I saw in your, on your lecture webpage that a lot, some of these parts have already been discussed. So I'm going to go over them quickly. So on the left, we have a diagram which shows that we have 6 nodes, and on these 6 nodes, we essentially have 3 data parallel replicas. So the entire model copy essentially is stored on a mix of 8 GPUs, right? And then when we zoom in to one single data parallel replica, we see that it can be composed of both pipeline parallelism and tensor parallelism, which means that the model transformer layers are sharded in a vertical fashion and in a horizontal fashion, right? So this is how these very large scale models are essentially deployed over aggregated GPU memory that is collected over multiple nodes. And then each node could look something like this, wherein you have multiple GPUs. So the gray boxes here denote GPUs, and they are connected through high-speed NV-links. And then each of them are connected through PCI to either the CPU or IO die, which essentially maps again to DRAM, to SSDs, and through network, it can go to persistent storage, right? So this is how a single node architecture looks like in the case of a lot of HPC machines. This specifically is the architecture of Argonne's Polaris supercomputer. Uh, and it has a memory and storage hierarchy in the fashion that is described in the figure here. So now the next question, now that we know how these models are executed, the next question is, what do we essentially need to checkpoint? What do we need to save, right? So I start off with explaining how does this work in the case of conventional deep neural networks, right? It could be a CNN, for example, right? So in this case, on the diagram on the left shows how the model and optimizer, which could be a simple stochastic gradient descent, right? How that is running on a single GPU, and when it is checkpointed, we just capture the entire state to checkpoint to the disk, right? And in this case, we have a pipeline parallelism of degree 1, a tensor parallelism of degree 1, and a data parallelism of degree 2. But what happens if we run this with a data parallelism of 2? So on replica, we see that there are two GPUs involved now, each having a complete model and optimizer replica. But what we can do is, instead of only asking GPU 0 to checkpoint its entire model state, we can leverage the aggregated bandwidth of both the GPUs and ask GPU 0 to flush the first half of its checkpoint and GPU 1 to flush the second half of its checkpoint, right? So this way we can exploit more IO bandwidth, which means the checkpoint would get completed faster. And then there are techniques like deep freeze and torch snapshot that are built on top of this. However, when we discuss the case of large language models, the story is slightly different because the checkpoints are now uh, argued in terms of transformer blocks or layers and not essentially in terms of the entire large model state, right? So on this diagram, we can see that this model is composed of two layers, layer 1 and layer 2, and that it is composed of an optimizer state. In the case of large language models, the optimizer state is something like Adam or Adagrad, which means that they are very huge in terms of size, right? So this essentially needs uh, a separate checkpointing primitive, just like every layer, and we cannot just checkpoint, let's say, a single number to capture the entire optimizer state like we could do in the case of SGD. So what happens here is that the diagram shows that the model is split across two GPUs. So it is operating with a tensor parallelism degree of 2 because the layers are sliced in a horizontal fashion. And the pipeline and data parallel degrees are 1. So what happens when we run this type of, or when we checkpoint this configuration of model running with a runtime like deep speed, is that again, the two GPUs, they will take half the responsibility of checkpointing, and they will essentially end up creating 6 files corresponding to these 3 data structures that reside on the GPU. And they again exploit the parallel bandwidth. So that is already pretty, that's the max throughput that we can get. And when we again replicate this large language model over 2 GPUs, similar to the case of torch snapshot, or similar to the case that we saw here with the conventional DNNs, the first replica would essentially be responsible for checkpointing the initial half of the model, and the second replica would be responsible for checkpointing the remainder half. So with that, instead of creating 6 checkpoint files, now on disk we have 12 checkpoint files because the data parallelism degree has increased, although the model remains same. But because we want to exploit as much IO bandwidth, we end up creating more number of files. So this enables highly parallel IO, which means faster checkpointing, but there are too many files, which may introduce IO bottlenecks because of metadata overheads on the shared storage system. So the goal, now that we understand how the LLMs are pre-trained and what data structures do we need to checkpoint, the goal is to create a highly performant, scalable checkpointing technique that masks the IO overhead that arise. So like I previously said, checkpointing has been studied in the past, right? So let me help you visualize how these IO overheads during checkpoint become a huge bottleneck. So on this diagram, on this slide, we see that we have something what we call as the synchronous data movement, right? So in iteration 1, which is labeled by a yellow box here, when the GPU computations are complete, if we need to checkpoint the data structures or the model layers, they are first transferred from GPU to the host. Then from the host, they are transferred to the disk, which is denoted by a purple block. And as you see, with increasing timeline, for a huge amount of time, the GPUs remain idle. And the same observation goes for idle GPU to host interconnect, and the same observation goes for idle host to disk interconnect. So because of this, if we run for two iterations, it takes a long amount of time for the training to complete. The next approach would be a partially asynchronous data movement technique, wherein we have the GPU computations going on, and then in a blocking fashion, we flush the data structures from the GPU to the host, which is denoted by a green box here. And then from host to the disk, these checkpoints can be flushed asynchronously while the GPU continues with iteration number two. So this is a very simple approach wherein we decouple the I/O phases with the training phases, starting from host to the disk. And this has been well studied in HPC. This is also one of the techniques that was described by Check Frequent, which is one of the state-of-the-art papers in checkpointing deep neural networks. And because of this kind of overlap-centric design, we see now that the execution completes a lot sooner. However, in the case of data states, we are trying to understand, can we reduce this gap even further, which means can we bring this execution timeline even closer to the completion of an iteration? And what we do is we start analyzing how the different model behaves, right? Behave when they are running. So on the graph, we see here that the x-axis shows different model sizes, and in the square brackets, we have different number of GPUs. And we see that as the model size increases from 3 billion to 70 billion, the size of the model that we need to checkpoint, it increases linearly. However, because we need more number of GPUs in order to run these models, the average checkpoint size per GPU remains roughly balanced. It remains the same. So in terms of load balancing, the pre-training takes care of it in a nice fashion. We don't need to really worry about it. The second observation that we make is that when we break down the iteration into forward, backward, and update phases, these are kind of the major phases that are there in addition to communication. But communication, in the case of LLMs, specifically with deep speed, are part of the backward pass itself. So what we observe is that more than 95% of the time during training, these model states are immutable, because in the forward and backward passes, the model does not change. The model only and only changes during the update phase, which is less than 5% of the entire iteration time. So what we do is we design these checkpointing engines based on these observations that model and optimizer states are immutable and the load is balanced across all GPUs. So with that, let me introduce the key design philosophies that we adopt with data states. So the first one is naturally leveraging immutability, which means that we keep copying until the next update phase starts. And only if we have not completed our copies of model states until that point in time, we will block the training. So this is a very proactive approach wherein we don't just stall the training for anything except when it is essentially needed. The second design idea that we propose is to coalesce the model and optimizer shard transfers to the host memory. So what I mean by that is we end up creating a buffer on the host memory that is pre-allocated, and it is pre-pinned so that from GPU to CPU we can transfer at the peak PCI throughput achievable. And then we optimize the host memory layout for bulk transfer of shards from multiple GPUs. And then we also adopt this principle of doing a streamlined multi-level flushing to persistent storage, which means that we don't need to wait until the entire model has been captured on the host memory. We can start streaming to the persistent disk as soon as a part of the checkpoint becomes available. And using this, we are able to use two physical links in parallel, the first one being GPU to host, and the second one being host to disk. And then lastly, we also need a consolidation consensus, which means that we need to make sure that all the GPUs have, or we have captured the data structures required from all the GPUs in a consistent fashion. And then we can commit that, okay, this model version has been essentially captured successfully on the parallel file system from which we can, restart if required. So with that, in addition to synchronous and asynchronous technique, we introduce a completely asynchronous data movement technique. So this, as you can see, uh, we have the iterations going on in a consecutive fashion without having any gaps in the timeline. And we can keep capturing from GPU to the host, which is the green bar here, while the next iteration is running. And then from host to the disk, again, can be decoupled and be done completely in the background. So as we can see, the execution completion time decreases even further. So this would be the fastest approach, but because of its overlap-centric design, we have multiple producers and consumers that need to interact, that need to signal with each other. That makes it challenging to design and debug. So this is what we focus on. And in order to give you a concrete idea of how this compares with existing approaches, state-of-art checkpointing approaches, we have four approaches outlined here. So what we see in this diagram is after we are done with forward, backward, and update phases for one iteration, the main training thread itself takes the burden of checkpointing all these data structures. And what it does is first it performs the transfer from the GPU to the host, and then from host to the disk, which is denoted by an orange blob here. So this would repeat for checkpointing of layer one, checkpointing of layer two, and checkpointing of optimizer state. And only when all of these are done and all the files are completely written to the stable storage, we start with the next consecutive iteration. Then we could adopt the partially asynchronous checkpointing technique, wherein we perform a blocking copy from GPU to the host. However, with these type of techniques, the challenge is that whenever we need to transfer from GPU to the host, we need to first perform a host buffer allocation, so they are not pre-allocated, and this is the case with check frequent, which is one of the state-of-the-art too, that we need to keep allocating memory every time we need to do a transfer from GPU to the host, and that way we can, the essentially the time taken to transfer also includes the allocation time. And on some of the modern CPUs, allocating this memory and pre-pinning it can be as slow as 4 gigabytes per second. So although the PCI can support 25 gigabytes or higher per second, the memory allocation overhead becomes one of the critical bottlenecks while training. So even when we have like two dedicated threads, one to do a transfer from device to the host, and the other one to do host to disk transfer, we essentially end up not completely overlapping all these transfers when we use an asynchronous approach, because the flushes to disk would start only when the entire model has been captured on the host memory, and the device to host transfer will overlap only the last data structure, which in this case is the optimizer. So it will only overlap the last data structure with the next forward pass. So this type of partially asynchronous technique doesn't work for the case of LLMs because they have multiple layers that they need to checkpoint. Then we study another state of art, which is torch snapshot. This was introduced by PyTorch itself. And the idea here is that every layer, so for example, L1, they will break into multiple chunks. So that way they can have like a piecewise transfer, which helps them overlap better. So every layer again gets broken down into multiple chunks, and then there are multiple threads that keep transferring from host to the disk in a parallel fashion. However, even this experiences the same problem that it first needs to allocate host buffer, then it can do transfers. And even if it did not, the blocking nature of transfer from the device to host, that goes in the main training thread, and we see that essentially the time taken to train uh, and checkpoint is a lot longer than that we would experience with asynchronous checkpointing. And lastly, data states LLM, which is our proposed checkpointing technique, what it does is that it will do a pre-allocation of entire host buffer as much as we need at the beginning. So this is a user configurable parameter that we have with the deep speed configuration. And then it can just keep flushing the multiple layers from device to host using a dedicated transfer thread, and only when these transfers are not complete. So as we can see the optimizer state here at the bottom, it still needs to be flushed to the host. So, we will not let the next update phase complete, because update phase would essentially modify the optimizer state, the model, because of which we might end up capturing inconsistent checkpoints. So, again, because of this overlap-centric design, and because of this notion that we only wait, or we only stall the training when essentially required, we achieve a much faster checkpointing and training throughput. So we implement DataStates LLM, and we with DeepSpeed. So it is essentially a modular extension to DeepSpeed. This PR has been approved. We still need to do some minor changes to push it to DeepSpeed, but hopefully in a couple of weeks, DataState should run out of the box with the DeepSpeed runtime. And it is written in C++ and CUDA, which means that it eliminates the inefficiencies arising from the global interpreter lock of Python, which is a big problem in distributed and high performance computing, because if the same data structure is referenced and by multiple entities, Python keeps a reference count, and that essentially needs to synchronization overheads. Um, and this can be, of course, extended to other runtimes like Hugging Face Nanotron or PyTorch Lightning. And what we do is we evaluate DataStates LLM on Polaris testbed with multiple models, multiple approaches. And what we observe here is that when we report the checkpointing throughput in terms of how many gigabytes get captured per second with DataStates LLM, we experience a much higher checkpointing throughput. And the way we define checkpointing throughput is for how long of an iteration, or for how much time was the main thread blocked. So we capture that time, and we capture the total size of the checkpoint. And when we divide it, we get the checkpointing throughput. So we can see that DataStates LLM outperforms other approaches by up to 34 times. And in terms of the figure on the right shows that in terms of the average iteration time, we end up accelerating the iteration by up to 4.8 times. Um, and then when we do data parallelism, like we previously studied with data parallelism, we end up using multiple parallel IO paths, and the size of checkpoint per rank essentially decreases, let's say from a 10 gigabyte per GPU to 650 gigabyte per 650 megabyte per GPU in the case of 13 billion model, and 870 megabyte to 30 billion for the case of 30 billion model. And in both of these cases, we see that even with a strong scalability, we have a much high checkpointing performance with DataStates LLM. And lastly, we study what happens when we increase the checkpointing frequency, that how this checkpointing frequency essentially means that after how many iterations are we capturing a checkpoint. So as we can see on the x-axis here, we end up capturing checkpoint after every one iteration. And even then, we do not experience substantially high checkpointing cost in the end-to-end runtime. So with this, the key takeaways are that running these distributed LLM trainings with hybrid parallelism strategies are prone to failure, might lead to undesirable trajectories, or might need administrative use cases for checkpointing, for which state-of-the-art checkpointing engines are not optimized. And DataStates LLM essentially proposes a set of design principles that can be leveraged in order to develop a much faster checkpointing engine specifically tailored for LLMs, leading to a 48 times faster checkpointing throughput and up to 4 times faster iterations. So with that, DataStates is an open source repository, so please feel free to clone it and try and contribute if you're interested. And then we also have multiple current and future research directions that we are doing in the case of LLM pre-training, in the case of inferencing. So for example, we have how can we optimize the GPU and CPU computations when the optimizers are offloaded to the CPU, wherein you are running in a constrained GPU environment. And we have a proposal that essentially performs smart overlapping of I/O and computations and achieves 2.5 times faster training as compared to state of the art. And then we are also studying what happens or how do we optimize I/O when we are running in an extremely memory constrained environment such that even the CPU cannot hold the entire model and optimizer, and we need to offload it to disk. So even with that, we are leveraging idle remote storage bandwidth, because of which we are able to perform these updates up to 3 times faster. And then with inferencing, we are studying how KV cache access patterns change under concurrency for regular dense models, for mixture of experts. And then we are proposing a unified dynamic model and KV cache offloading technique such that you can run inferencing on a smaller subset of GPUs while achieving the same throughput that you would with more number of GPUs. And then we also have other works like studies on evaluations, or how do we do elastic reconfigurability with DataStates LLM. So yes, we have lots of interesting topics to work on. So feel free to reach out if you'd like to work on some of them. And with that, I would like to thank you all and open for questions.
I'll start with a basic question or a naive question.
Yeah, sure.
Are there solutions that let you copy data directly from disk to GPU memory, or you always have to go through the CPU?
So there are solutions like GPU direct storage. However, not a lot of HPC facilities have, at least in the case of Argonne, they have not enabled it because it requires some kernel modules, and I think they're still kind of trying to evaluate how those proprietary NVIDIA kernel modules might impact their